Hey guys, I'm doing a new video here and I'm calling it the Petabyte project. It's an absolutely ridiculous project that has no possibility of doing anything close to what I think it will. I'm sorry, I've got my camera in a weird spot. Anyway, this is the Petabyte project. It's basically a stretch goal for me to try and learn as much as I can about big data analysis. So I've moved from watching these big data lectures to just sort of having this idea of creating the ability for people to iterate through big data on my platform. So yeah, that's really my goal here, is to be able to create a good platform that hedges against these really big systems like AWS. Um, and I sort of had this realization as I was watching this lecture, which I can show you the actual lecture.
All right. Hey, everyone.
I'm watching this lecture, not on this account, and I'm just thinking, holy shit, a lot of this stuff has been done. Not referring to my platform, but a lot of the things I thought I would have just a little bit of on my platform, like storage, and my cloud platform would be storage. I really don't need to reinvent the wheel. I'm trying to build this platform quickly and in an agile way. And the reality is, I don't need to rebuild a lot of these common functionalities because they've already been really like mass adopted, mass created, and scaled to blitz. And to try and compete with that is ridiculous, and it's actually like against the consumers I'm trying to serve. So my thoughts are, you have a little bit of storage to work with in each YDP project, your data place. You have a little bit of storage to work with in each of them. But if you want to use big data, I will provide a tool set, which I'm actively developing out now, in order to try and increase that sort of product offer. So one of those is polytrace and iterators. So my thought around these ideas is that I want users to be able to interact with their big data in just a comfortable environment. I don't want people to have the stigma of a whole new framework just to even look at their data. So these introducing these ideas, iterators, polymorphic structures, like everybody knows what they are, but I'm introducing them because I feel as if they can sort of be used in this platform to speed up things. So for example, polytrace is the concept that you can write some code and that code is fake, and it makes you think that you're interacting with the data, but you're not actually. So I'll give you an example just really quickly. So here is an example of polytrace with a really basic implementation in Python. What we have up here, and you can sort of ignore all this, I'll just cut it out for now. What we've got up here is we're importing polytrace, which is a class. We're then creating a variable called big data under polytrace. And then this is where YDP ends. So this is all YDP header that is automatically loaded in to the project. And this is the user provided code, so which is an iterator over that big data. And this is another YDP start. So just ignore all this code. This would be something provided to YDP. Imagine you open up a Your Data Place project, create a file called names, and then you're able to instantly import your big data. Could be gigabytes, could be terabytes. And in the case of the Petabyte project, I'm trying to create infrastructure that can manage petabytes of data. You can import that, write code to do something with it, and then you just think that code's running. So the idea of the Petabyte project is that big data objects can be managed behind this really simple Python code, can be managed behind the scenes. Petabytes of data can be managed behind the scenes. So for example here, I use this example here, where this is something the user provides. We iterate over rows in big data. We get out the ID, and this is what each row looks like in our iterable big data. We get out the ID, we get the user data here in user data. We then extract out the name, Jack Hales. We also extract out the age, 22, and then we append it to this age here, and then we calculate the average age and save that as a variable. So now what we've done is we've linked up a ton of data, could be gigabytes, terabytes, like I said, likely won't be. We've used all these YDP tools. We've then taken user code that they think is running their function, and we've used Python built-ins in order to be able to craft around that and access what they've accessed. So if I run this test code here, bigdata.capture down the bottom, bigdata.capture here, that is going to print out this, which is the accessed variables in each row, iterable row. So for this, we went name, row 1 name, then we went in 1 age, and then we went in 0. Now what we can do is we have this data from the user. They think their data is going to be iterated over, even though this does nothing. Now what we can do is we can stack that with an indexing algorithm to only get those fields from our large data set. So we may have an extremely complicated database. We may be using some legacy JSON that has a really weird polymorphic structure. By indexing by just these indexes, we can start to get exactly what data we need and dramatically reduce the search space down and the iterable size radically. So they think they're iterating over every single row, but some optimizations can be easily made in order to split this data up into its polymorphic components and just iterate over those parts. So that idea struck me watching this lecture. I keep removing everything. That idea struck me on this lecture, and I just had to sort of play around with it. And that's where the petabyte project came into place. So that's cool. We've done some theory, but now I wanted to start setting some base benchmarks that we have to beat. And the first one I'm trying to play around with was actually iterating over a petabyte by starting with a gigabyte. So we're trying to clock how fast we can iterate through a raw gigabyte. And what I've done, so I'll have to look over my microphone, is I'll just grab up, I'll just go back to polytrace real quick and talk about the class. Yeah, you can see here, this is this code here. Polytrace, we create that class. It knits itself with rows and poly access. And then we define an iter, which is what runs here. We only run it once. Then every time we get an item, which is this start of a sequence, we want to create a poly access with that key, which is 1, 1, and 0. And we want to append them to the poly access variables with the key and the poly access. The key and the poly access object, and then return PA, so we can keep doing that, keep running down. And poly access itself is another class. And we have the context index, which is where it starts, and the access history. And every time we get an item there, we append it, and we return self, and then it's not a callable thing, but whatever it could be. And then bigdata.capture just iterates over these keys and poly access objects. I did ask a member of the Polynesian community, and they did say that I am able to use poly because it doesn't mean Polynesian unless it's used that way. So that's a big win, because I couldn't think of anything outside of polyaccess. That's me, by the way. Absolute epic photo. So moving on, I started, and I'm just going to quickly switch over to the Gigabyte Iterate project. So now we get into some benchmarking, and we start off on Windows, like most projects unfortunately do. We start off on Windows. We have a gbtest.csv, which is a really large CSV file, which just has name and age, Jack Hales, and 22. Again, theoretical. I will do this on test data once it's a bit further, but just for the sake of this, we've done that. It makes it to about a gigabyte, and then it saves it as gbtest. This is a terrible script. I wrote it very quickly. This, on the other hand, we've got some tests. CSV reader takes 23 seconds to iterate through a gigabyte, which is forever. Running through lines in open takes 10 seconds, and chunking it is a lot quicker. It's 3 to 4 seconds depending on chunk size. Optimal at 64,000 bytes, whatever. And here we start playing around with chunk sizes a bit more in a different implementation, sort of, and I'm using perf counter and a best, and I was using an iterator to find the best chunk size. 65,000 seems to be good. Something to do with 64-bit, maybe, I don't know. But if we run this, we will get 65 chunk, took a flat 3.78 seconds to iter. Best is that, which is cool. But if we forecast that out, as per I wrote in the article, if we forecast that out, that will take us 40 days per petabyte to iterate. So to refresh just on the goal is to do that in a few minutes, which is ridiculous. I started to realize, but we want to iterate through a gigabyte in about 0.0003 seconds, and our current clock time is 3 to 4 seconds for just a raw iteration, having the chunks accessible in a variable. CSV goes a bit further, that's why that takes longer, and raw, whatever. But yeah, those chunks are provided. But as you may have seen, I decided let's try this on my M1 laptop, and the time was insane. Insanely different. It took about 0.13, 0.14 seconds per gigabyte, or 0.12 I think was the best, and that is extremely fast. So we've brought our gigabyte iteration time down from 3.4 to about 0.12. That brings our days per petabyte from 40 days to 1.5 days, which is great. And from there, you know, that's sort of where we got to. I was extremely confused because of the result comparisons. We've got, these are the crystal disk mark results. That's my M1 here. No idea why this is occurring, but so be it. Let's have fun with it. And from there, I decided to jump onto my Linux machine, and let's see if I'll make that a bit bigger. Yeah, just make it the whole screen. How about that? Yeah, very fun. From there, in the Linux machine, I thought, let's try it. So as you can see, we've got just about a gigabyte, and we do Python 3 dummy iter.py, and what's going on here? Oh, I think it's running the CSV, which takes forever. One sec. So now let's write dummy iter. Took about 0.5 seconds, so still 6 times quicker. And with optimizations, I was able to get it down even more, as in changing the chunk sizes. But you can see, I mean, with 3.9, 3.8, 5.8, I mean, the average is probably 0.4. So, like, dramatically bigger and quicker than Windows. I really don't know why that is, if I'm being honest with you. I would like to say it's OS, but there's probably something I can change in Windows. Apparently Defender could be a culprit, but I mean, it's a very clunky OS. Anyway, obviously, Linux is the best benchmark, and the Mac is obviously a weapon. So from there, that's where we sit with the Petabyte project. I wanted to make this video just as a way to brainstorm what I'm up to and what I'm playing around with. Obviously I haven't stopped my wish for YDP, but I thought I would just take a bit of time to get myself more acquainted with different systems, work with I/O, big data, because I presume the compute tools will be really helpful and useful, not just for myself, but also for all developers in big data. Because, everybody wants to work in this sort of scripting world where you can just write a simple script and have it iterate through big data. And the Petabyte project is not meant to set this example for you want to iterate through petabytes of data. Instead, it's trying to set the worst case as better, making the worst case better. Because I don't want the worst case to be 40 days. I want to bring that down as much as I can, and by setting a stretch goal for 5 minutes, that helps a lot. That's what I've been playing around with. This is the article I wrote that corresponds with this video. I'll be editing the article as it continues and I get more information and play around more. I just sort of wanted to take the time to talk about that. I don't think there's much else. I might talk about poly-indexing real quick. I'm just going to grab another project real quick. So here is poly-indexing. It is the test that I set up for basically, there's a lot of different poly projects, but anyway. Once you turn your JSON into an iterable, which you can do by either chunking and then looking for the tree graph, once you start, if you're in a key value JSON or an array JSON, you can mark where the iterables are by using an iterable JSON parser. Anyway, that's unrelated. If you have those iterables, you can then attempt to index them as objects, sort of like MongoDB. So here we have an array of objects in JSON, and this is the object example. But what we can do is we want to turn this tree graph into an index. I haven't seen this done before, but I would presume it's been done before. But we have Jack, which goes into age and rate. I don't know what these were referencing when I wrote it, but Apple goes into 1, okay, A, B, C, D, blah, blah, blah. Just a weird, wacky tree graph in JSON, and we want to index it. So running this code, it gives us this string, which can be optimized for sure. It gives us this string, which says object of 3. First is Jack, which goes into an object of 2, which has age, which goes into an item, and rate, which goes into an item. Now that's true, right? I don't know if you can see my cursor. Anyway, next is Apple, and Apple goes into an item, and that's it. We're still in O3, the root 3 objects, and then we go into OK, which is an object of 1, which goes into OK, and you get to see how this builds out a unique index for this iterable object, this entire object. And what it does, I just closed it like an epic man, is then you can create this, which is the values. So the first age, is 21. Rate, 100. Apple, 1. So forth and so forth. 1, 2, 3, 4 is after that, which is 1, 2, 3, 4. And we build, we decouple the polymorphic structure from the values themselves. And again, don't know if it's valuable, don't know if it has anything to do with the petabyte project. Just a really cool tool I wanted to look into as a developer myself, because then what I thought is this could be stacked with polytrace to take what the user is trying to get, and maybe that's whatever. It might be all of these, A1. Instead of iterating through every single of these iterables, you can just go into a certain file and all of them are there. That's the concept. All of the, sorry, all of the iterables will be under this index. Then each of the values will be in a new file. And this is an idea I've just come up with on the spot, to be honest. Like, that's nuts. That's a crazy idea, to have column-oriented files. That's nuts. And then you can iterate over that specific polymorphic piece in the entire iterable at once. So you go for this example, you could go for, and actually, you know what, this will be fun. We'll do it in our other file. I got rid of all the comments. I'm doing this live, but what we can do now is we can go for row in big data, and we can go, I want this A here. So what do? I go, or we'll say item to use the same terminology. We go row, and we're starting from here. So we go, okay. Oops. Okay. And then we go into A. And if you honestly print item, it's not... Yeah, we can see, okay. We have the polyaccess object. And when we call big data capture, we go okay, A. Now these two different projects don't map up in their schema, but that's something that could be engineered for sure. And then with that, what we can do is we can take this data, send it to a cloud or a stream. That will then fetch the corresponding files, zip through the data, tuple them up, and pass them as a generator through the stream to the big data object, which we can rerun as like a poly provider, and we can go like okay, A. And give it a whole bunch of those, and it will then create a schema which is custom to what they're going to access. So that would be something that literally just looks like okay, A. And then when they run item, that's just going to be 1. So yeah, again, I don't know if this is valuable. There could be some constraints in when I try and implement this in production, but I think, yeah, it's an interesting idea to play around with. It may relate to the petabyte project. If I create like a petabyte of iterable JSON and then start caching it and index it, then iterate through it using this method. But as you can see, yeah, this is the concept I'm starting with and playing with. And yeah, I hope you found it interesting. So, yeah, check out the blog, yourdataplace.com. Search for it. Maybe you can find it, maybe you can't. Check out YouTube channel, all that stuff. Yeah, give it a follow. Very early stages of the platform, but really wanting more feedback for sure. I've got a few bits of feedback from a few people, but definitely always good to have some more. Anyway, guys, thank you for watching if you've stayed this far. It's been a lot of fun speaking through this idea out loud. And yeah, we'll definitely be working on this a lot more, trying to get to a petabyte in iteration, and I'll be definitely back soon to do another update with hopefully some insane improvements. I mean, yeah, I've already improved it by just moving it to a Mac, so that's good enough. But yeah, awesome. Thanks for watching, guys. Subscribe.